In this problem, we're going to take silver nitrate and sodium chloride and combine them and form silver chloride. In this case, we put 0.57 liters of 0.25 molar sodium chloride. We put 243 milliliters of a 1.5% weight to volume silver nitrate. So I have two starting amounts of starting materials. What I want to know is what is the max silver chloride that could be produced by mass. Go ahead, see if you can puzzle this one out, and then come on back. All right, if you're back, well, I have two real amounts stated of starting materials. This means one of them is not going to be enough. This is a limiting reagent problem. In order to solve how much product I will make, I need to know which of these I don't have enough of. Luckily, the process of figuring that out will actually tell us how much product we make. We need to take the starting amounts of each and use that to find what is the maximum each could produce of our silver chloride. Whichever produces less, that was our limiting reagent. To start with, I have 0.57 liters of my sodium chloride solution. So 0.57 liters NaCl aqueous. And according to the molarity, in every 1 liter of the solution, so the aqueous sodium chloride, there should be 0.25 mole of the chemical. Well, I need to find my silver chloride, so this isn't done. I need to carry this on. Once I would divide and multiply, I would have found the moles, but the moles of sodium chloride need to be converted to moles of silver chloride. My balance reaction says it is 1 mole of NaCl for every 1 mole of AgCl. And so far I've managed to cancel my liters of solution, cancel the moles so that I'm in moles of sodium chloride, so I'm in moles of silver chloride. The final question, though, wants the mass of silver chloride, so I need to get out of mole of silver chloride and into grams of silver chloride. Well, molecular mass up above says it's 143.32 grams per mole. If we multiply all those and divide by ones, we will get 20.423 grams of product is possible. If we do this for the silver nitrate, well, this one didn't come in molarity. This one came in weight percent. So we need to adapt it. We need to convert it so that we can get to moles. What this tells us is that there is 1.5 grams of silver nitrate in every 100 milliliters. Well, I'm using 243 milliliters. And so if I was using twice as much, I would have twice as much weight. I'm using a little over twice as much, and so I'm going to have a little over twice as much weight. What we'll find is 1.5 times 243 divided by 100 gives us 3.645 grams of silver nitrate. So I know my weight of silver nitrate that I added, 3.645 grams of silver nitrate was what was added to the solution. I can get out of grams of silver nitrate and into mole of silver nitrate. Up above, we have the molecular mass listed. It's 169.87 grams in 1 mole. And so that'll let me cancel out my grams of silver nitrate and get into moles of silver nitrate. But I don't want to be in moles of silver nitrate. So I need to leave moles of silver nitrate. I want to be in the product. I need to be in moles of silver chloride. Balance reaction still said it was 1-to-1. And so I can get out of my moles of the silver nitrate starting material and say, hey, whatever number that was, it's the exact same number of my product, silver chloride. And again, I need to get out of mole silver chloride and into mass, because the problem asks us for the mass of the product. So in our case, 3.645 divided by 169.87 times 143.32, we will find that this is 3.075 grams of silver chloride. What we find is that is significantly less silver chloride. We don't make anywhere near as much using the silver nitrate as we would if all of the sodium chloride had reacted. So our limiting reagent is whichever chemical makes the least product, and so our silver nitrate is our limiting. This means the max possible silver chloride, well, we had 2 sig figs, so this would be 3.1 grams of silver chloride is possible. That is the most we would expect to make. Now, why did we make so little? Why 3 versus 20? Well, salt is cheap and easy. You can easily have very concentrated salt solutions. Silver-containing salts are a little more expensive. It's silver. Why might you have a bottle of 1.5 weight to volume silver nitrate? Babies. We don't think about it too often, but in the modern world, most places use erythromycin and other type of antibiotics. When a newborn is born, they put it in the eyes to kill any bacteria. Infant blindness was actually a terribly common occurrence in the old days in the past. When the mother gave birth, any bacteria and anything else could get into the baby's eyes, still can, and we didn't have antibiotics. If they were aggressive, gonorrheas and chlamydias or anything like that, it would blind the child. It was discovered that a 1.5 to 2% solution of silver nitrate, well, it has antibacterial properties, and so it would kill the bacteria, but didn't harm the eyes enough to cause any damage. And so we'd put these drops in babies' eyes. These days we use antibiotics, but if you don't have somewhere you can refrigerate, it is still not terribly uncommon to use silver nitrate, because the salt can just sit forever. It can store in warm climate and humid conditions, and it's just fine until you want to mix it up to use it. So in more remote areas, shipping out silver nitrate is actually a much more effective method than trying to get antibiotics out. If anybody ever does Doctors Without Borders or something, you might run into this still. Danger becomes if you use too concentrated a solution. If you mix up a 1.5% solution and then some of the liquid evaporates, then it becomes more concentrated. Well, then you have a 7 or 8% solution. If silver nitrate gets more concentrated, it tends to dye human skins black for a while. And so pure black eyeballs on a child is probably not a great thing. Additionally, it can damage the cornea and cause blindness if it gets too significant. But this is where you would find a 1.5% solution, and why they might have had it handy to try to make this reaction work. In this problem, we're going to look at an acid-base reaction. And so I have sodium bicarbonate. I'm going to add sulfuric acid. This is going to make sodium sulfate, carbon dioxide, and water. If you've ever made a baking soda volcano, well, sodium bicarbonate is baking soda. So you throw an acid like vinegar, not sulfuric acid hopefully, on it, and it bubbles and foams, and this is what the CO2 is actually doing. It's those bubbles, the gas that emerges. What we know is that we had a 3.5 molar HSO4 solution. We added 100 milliliters of it to a container. I then started adding sodium bicarbonate. After 122 milliliters of sodium bicarbonate solution was added, we had made 1.1 grams of carbon dioxide. So the question here is, what was the molarity of the sodium bicarbonate solution? So we're actually going to solve a molarity this time. We know the volumes, and we know some of our balanced reaction. Well, not balanced yet. And so 2 sodium bicarbonates, 1 sulfuric acid makes 1 sodium sulfate, 2 carbon dioxides, and 2 waters. So how do we determine the molarity of the sodium bicarbonate? Well, I know the amount of CO2 I produced, 1.10 grams of CO2. I can find the moles of it, because you always need to find moles. If I'm going to compare 2 chemicals, you need to find moles. It is 44.01 grams in 1 mole. And so we'll find that 0.02499 mole of CO2 have been created. Well, if I know moles of a chemical, I can find moles of my other chemicals. And so 0.02499 mole of CO2. Balance reaction says for every 2 mole of CO2, I must have had 2 mole of NaHCO3 of my bicarbonate. So it's the same amount. I must have had 0.02499 mole of sodium bicarbonate. When I reacted that 122 milliliters of sodium bicarbonate with the sulfuric acid, it produced this much CO2. So by knowing the CO2 I made, I can solve the amount of bicarbonate that must have reacted. Well, that bicarbonate was in this volume. So I know the moles of bicarbonate and I know the volume it came from. And if I want the molarity, I need moles and volume. So I have 0.02499 moles of sodium bicarbonate in 0.122 liters of solution. Now, that 100 mils of sulfuric acid, that's not part of the bottle that sodium bicarbonate came from. All of the bicarbonate came from the 122 milliliters that would have been poured out of its own bottle. And so the concentration that would have been in the bottle, the concentration of sodium bicarbonate originally, is the moles of bicarbonate over its volume. And so if I divide those, we find 0.205 molar NaHCO3. What concentration would the sodium bicarbonate have had to have been so that 122 milliliters would make 1.1 grams? That solution would have had to have been 0.205 molar. And so we can use concentrations and stoichiometry to calculate out not just what volumes of a chemical are needed, or what masses are needed to make something, we can also find out for the amount we added, what was the concentration. If I know the amount of product made, I can solve the amount of reactant needed. If I know the volume that reactant was in, then I can solve the concentration it must have been.